Yeah, comes on everyone. Let's start off. Yeah, so last thing we did was this temperature of the sun surface. We also did the parallel plates. Great. Let's go ahead with the problem. If you see the last 3-4 problems that we did are actually like advanced level questions. Should I revise them? In case you didn't do it again today. Others do keep your cams on. Yeah, let's go ahead with this. What is this? 20, 21. A spaceship in vacuum is maintained at 500 Kelvin due to heat generated by internal operations. So when you have a spaceship, right, maybe the engines are switched on, or maybe when the internal machines are working, something, whatever is the reason, the heat is being produced inside. It is all internal. So basically, it is like kind of there's a heater inside. So we have a spaceship. Outside is vacuum, so there is no surrounding temperature. So the internal operation, so heat is being generated. And because of this, the surface temperature is 500 Kelvin. So what is happening is, whatever heat that is generated here is escaping from the surface now. Think about it. Suppose initially, internally, if there is no heat generated, the spaceship will keep on radiating heat and eventually it will cool down to 0 Kelvin. But the temperature is maintained at 500. That means whatever heat is escaping from the surface is equal to the heat generated internally. Now, how is heat generated internally? We're not worried about that. This part of the story is clear. Everyone. Now what you did, now the spaceship is covered by E is equal to 1 for the spaceship. The spaceship is covered by a shell of 2R radius. So we have the spaceship. Now you took a shell concentric and you kept it here. Radius is 2R, E is equal to 1. Now the spaceship is still generating the heat and everything. Nothing changed for the spaceship. Now think about it. Tell me one thing. During winter, when it is pretty cold, why do you put a blanket on yourself? When you put a blanket, why does it feel more warm? Because you're not letting all the heat escape out, isn't it? Some of it comes back to you. The same way, when there is no blanket, temperature is 500. Now, if you put a blanket around the spaceship, don't you think it gets more warmer inside? So the temperatures won't remain at 500. Something will change. So find the temperature of the shell and the temperature of the spaceship when the blanket is covered. In steady state. Again, steady state meaning net flow must be zero. Whatever is coming must go away. Again, listen to the whole story. You have a spaceship in vacuum. Temperature is 500 Kelvin. It is maintained by internal heat generation. Now the same spaceship, when you go and cover it with a blanket of radius 2R, something changes and the temperatures are not 500 changes. So what is the temperature of the shell, the outer shell, and the temperature of the spaceship? This would be an advanced paragraph question. I'll ask you these only: temperature of the shell and the temperature of the spaceship. Did everyone got the story? Scenario is clear. Anyone didn't understand what is happening with the question, ask me. Question is clear. Go ahead. Think about it for a minute or two. Then I'll give you a little hint, and then again I'll give you more time. You think whatever it is for a minute. Temperature of shell is still easy. Temperature of the ship requires a lot of little work. Anyone not convinced with the question, please ask. Tell me one thing. When you cover this with a blanket, what remains constant? Without blanket, with blanket, what remains constant? You need to always think, whenever they give a question, not only this thing, any question, always ask yourself, when this situation happened, what remained constant and what changed? Right, Janil. That is important. You need to think always. And you don't think what is constant, what is not constant, you'll not understand where to look for. It'll be like, you're just looking randomly everywhere without understanding. It's like this. If I tell you, Arey yaar, I lost my mobile phone, what is the first thing you ask? Where did you lose it, right? Without that, you randomly go and start searching in your house. Does it even make sense? Most of the people have that problem. They don't even think actually, okay, something changed, so something remained constant, something is changing, or did everything change? What do you guys think? 10 seconds I'll give you. What remained constant? Generally got the answer. Anyone else? You can type in the chat box to the co-host. Covering the whole thing with a blanket, what didn't change? And don't tell me radius of the spaceship, I'll punch you. Give me something more reasonable. That Pratik is about to type that. The amount of heat generated by the spaceship, right? Whatever heat the spaceship generated before the blanket is covered, you still generate the same amount of heat, isn't it? Why will the heat generated by internal operations change because you are having a blanket outside? Is that making sense? So before the blanket, whatever is the power generated by the spaceship, you'll still generate the same power even after covering with a blanket. Did that make sense? Now can you try? I'll give you a minute for temperature of the shell. You have to start from the shell. See, now my idea is what is the power radiated from the surface? So can I say like this? The power radiated by the ship, this is sigma AE 500 power 4. This must be the power escaping, or you can say this is the power generated internally. Let's call this value P. And this is constant. Doesn't make sense? whatever heat is generated inside must be escaping through the surface of the spaceship because it is in steady state. See, whatever is coming from inside, if it doesn't escape to outer space, then what will happen? The shell cut temperature will keep on increasing. If the shell cut temperature increases, it will emit more and more heat. At one point, the heat generated will become equal to the heat emitted, so you reach a steady state. That is the first part. Now, second thing, we agreed the heat generated inside is still same, power P. Now, I don't know what is happening between them, right? But one thing I'm pretty sure, some heat is escaping from the outside. Now, because this is in steady state, can I say like this? The power radiated by the shell must be equal to, right, the power generated inside. Whatever is happening between them, that is fine. But if you see the whole system as one thing, if I take the whole shell plus this thing, what is the total heat generated inside? P, na? And all the heat escapes to infinity from the outermost shell. Shouldn't these two be equal? Because if these two are not equal, that means some heat is getting stuck inside and the temperatures inside are increasing. So this is not steady state. Is this making sense, everyone? Whatever heat generated by the spaceship inside must somehow escape from the outside shell to infinity. This would be how much? Sigma AE. Area will be sigma. Area will be 4A because radius is 2r. Area is 4 pi r square. Temperature is T shell power 4 is equal to power generated internally is sigma AE 500 power 4. Equate them, you end up with 4 times T shell power 4 is 500 power 4. So T shell will be 500 by root 2 Kelvin. There. That would be the temperature of the shell. So basically this is equal to P. So whatever power you're generating internally, all that power should escape from the outermost shell, which is also equal to P. The radius has become 2r. Now how to find the temperature of the inside surface, the spaceship? This part is clear. So advanced paragraph, this will be one question, which is easy to manage. The second part, they'll always make it tough. Paragraphs are generally like that. One question will be easy and one question will be little work. Think, now what to do? I'll give another minute or two. First, be clear with this. Anyone didn't get this page, please ask. Let's see. Shell has two surfaces or one surface. You tell me that. You can clearly see here how many surfaces it has.
So one, I think.
One. So, Vihan, let's say tomorrow you started a paint company and I give you a contract to paint my house. Right? You'll come and paint only the inside and go away. Should I pay you like for how much money? Should I pay you for both the walls inside and outside, or should I pay only for one side? You should try contacting a paint company. They'll come and just coat it inside and they go away. Or they just coat outside and go away. You paint inside and outside. There are two surfaces. So listen to this thing. This is something different you should know. So this concept, right? Mostly they should explain in a paragraph, or they might can't. They might leave it for you to figure it out. Now look at this thing. When you have this outer shell and you have this inner one, there's a catch. If this radius is r, small r, and this radius is capital R. Now tell me one thing. When you switch on the light, the bulb, when you switch on the bulb, the light goes in which direction? every direction. That means when a body emits photons, there is no guarantee they will go in one direction. The photons are coming in every direction. So they're going like this, 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 they're going like this. Did you see what happened here? Whatever comes from outside to inside, everything doesn't fall on the inner shell. Some of it goes back and fall on itself. Is that making sense? Whereas in reverse, whatever the inside one gives, everything will go and fall outside only. You will never have a situation where this will come and come back like this. Na? You can't go and fall on yourself. So whatever the inner shell radiates, everything will be taken by outside. But whatever the outer one radiates, only a part of it will come and fall. So the formula, right, is this. So power received by inner shell is power by outer shell into area of the surface area of inner shell by surface area of outer shell. So it depends on the ratio of area of the shell. So power on the inner shell. So everything the outer shell gives won't come inside. This would be 4 pi r square by 4 pi capital R square. I mean, our question, small r is r and capital R was 2r. P outer into r square by 2r whole square. That would be P outer by 4. This is the first thing you should know. That whatever energy the inner surface gives, right, everything won't go and fall on the middle shell. Some of it will go and some of it will go and fall on itself. Is this making sense, everyone? Because photons have no specified direction. When you switch on the bulb, you can't tell the photons, all of you go in this line, isn't it? The photons will spread out in all 360 directions randomly everywhere. Yeah, but they do go uniformly in every direction. So it kind of based on the surface area there. Now, from this logic here, now if I go and draw this, so this is the outer shell. This is my spaceship. This is the temperature of the shell. So this guy is radiating heat outside. Sigma area is 4a e t shell power 4. And if you remember, we actually proved this is P, isn't it? That is P. So this guy also radiates. Do remember, everything is not falling here. Some of it is going that way. This would be P by 4. And also, you're generating power internally. That is also P. On top of it, this spaceship is radiating heat in all directions, which is sigma AE, temperature of the ship, power 4. So if I just see the internal one, you will notice this. So you're getting inside, it's a power P. From outside, you're getting P by 4. This is all the energy that you're absorbing. And you are emitting out sigma AE T ship power 4. Is this making sense? So if you look at the spaceship ka surface, the spaceship ka surface is getting heat from two places. One from inside, which is P, and one from the outer shell, which is P by 4. It absorbs all this because you're in steady state. This should be equal. So power received by the spaceship must be equal to the power emitted by the spaceship. So how much you're receiving? You're receiving P internally and you're receiving P by 4. This must be equal to sigma AE T ship power 4. This is 5P by 4, but what is P? P itself is sigma AE 500 power 4. So we have T ship as 5 by 4, whole to the power of 1 by 4, 500. Check. So what makes the second problem tough is this part, figuring out that all the energy won't fall on the inner shell. Only a part of it will fall, and which will be in the ratio of surface areas. The more area, the more energy it will receive. Meaning, just to give an idea of this, the actual JE question was this. The actual JE question is there is a spaceship, someone covered it with a shell of almost same radius. Then what would have happened? Everything that is emitted from the outer shell will fall on the inner shell, right? So this was actually JEPYQ. So they made it your life easy by giving this. But what if the shell has a radius? Now we have a problem. Everything won't fall. So have a look at this.
So can you please show the previous page?
Hmm.
Thank you, sir.
Anyone not convinced with this? Anything that you are not clear, please ask. Clear? Any doubts on this page? It's a pretty good one. You should try it on your own again. Meaning, if I ask you like this, you can try this as a homework if you want. Just a problem like this. There are three shells. R, 2R, 3R. Let's say temperature of the inner shell is 2 T naught, temperature of the outer shell is T naught. Remember the three plates wala problem? Instead of plates, it's shells. Find the temperature of the middle shell in steady state. Something of that sort. You can try that as a homework. So that's what I'm saying. You can always create questions out of your own cell, but yeah. You can try that. That will be a little complex. Assume E is equal to 1 for all surfaces. I will leave it. You can try and see. I don't know the answer. I just made it up. Clear with this? Let's go ahead. Next one. Next one. Now, this is called a cube square law. Quite an important one. If you ever heard about it, it explains a lot of things. It explains like why you can't design a motorbike engine in a certain way. Basically, this thing limits the power a bike engine can give. This also tells you about architecture buildings. This even tells about how animals evolve. For example, it's like, what is the largest land animal that you know? When I asked this in the class, someone shouted Sudhir. There is this guy in the class, Sudhir Garg. He's a little big. So someone shouted from the back, Sudhir Garg, the largest land animal. I said, okay. So, and some sort of the elephant, right? The African elephant is the biggest one that we know of right now. What is the largest sea animal that we know, or a water animal? A blue whale. So if you think about it, a blue whale is almost like 50, 40 times bigger than an elephant. So that means animals in the sea can grow much bigger, but somehow the animals on the land got limited. And if you think about it, the bigger the animal, the better, isn't it? Evolutionary wise, if you think about it, if you have a larger elephant can fight off the predators more easily. A larger elephant can get more food. A larger elephant can dominate more. So basically, a larger elephant has a a better chance of survival. But there is a problem. We have seen in nature the elephants don't grow beyond a certain size. They are limited. Like it's done. Getting it? So something is stopping them from growing. Getting it? So there is always that some kind of limitation there. Now, this happens a lot in multiple things. For example, if I had to give you another thing, normally when I teach for medical batches, right, we talk about a lot of stuff about evolution and all that thing. Because as medical people, if you teach them pure physics, they go mad. They feel like, why do we need physics for biology? I tell them, bloody, your entire body, right? It is physics. The blood that is flowing is fluid mechanics. And you get a fever, you're talking about thermodynamics. And you guys don't want to study this. So when they really don't understand the processes, I tell them that only. You'll just become a a hopeless doctor sitting in some corner in some street and writing medicines for headache and fever? Is that the type of doctor you want to become? Then they get offended. That is a fact. If you don't think about it, if you are just a mindless thing, then there's no point. So then I tell them a lot of things. So one of these things that we discussed, right, was this: the size of a human brain, the size of a human skull, you can say. Now, this what this archaeologists found, right? When you take up a person ka skull from 1500 years or 2000 years back, and if you compare with the modern person, you will notice the size of skull is bigger, meaning almost like not. Again, I'm not saying the heads are like big heads or something. You won't become like aliens. But the thing is, like maybe we are 10, 5 to 8 to 10% bigger than the previous ones. The reason is simple. People with a bigger skull can accommodate a bigger brain. Bigger brain means you have better communicative skills, you have more intelligence, you can think better, you can stay alive for long, you can have better resources. So you have, since you're living for longer, you can pass on your genetic material more easily, right? So your offsprings, there is a high chance of surviving. So end of the day, evolution, right? Again, people have this misconcept. Evolution meaning it doesn't mean you're stronger. It doesn't mean you are faster. Evolution simply says the one who can adapt easily will survive longer. Evolution has nothing to do with a stronger and a faster animal. Evolution is always about who survives longer. So then these people notice the human brains. This is the thing. So the size of the human brain with the time. So when you plot this, they notice it is increasing. Generation after generation, it is increasing. This now I saw it not skulls exactly, but when I saw you students, right? The students, when I taught them, when in my first year, 2010, 2009, when I started, right? The students in 11th and 12th, they really used to look like kids, meaning they used to come to my shoulder ka height, right? Kids only. Now, if you see, some of you are taller than me. I come to your shoulder. Then this thing I observed, right? Kids are like going taller and taller and taller. The average heights have gone up. My parents are shorter than me, right? I'm taller in my generation, and the next generation is taller than me. So something is there. Maybe we are getting better resources, right? So there's a thing. So this is what they noticed. The size of the skull, right, was increasing, 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 increasing. Again, not drastically. We're talking about 10% something. And then somewhere around 1920s and 1900s, it became constant. And then in 1980s, it suddenly again started increasing. What do you think happened? Skull took a break. Skull went for a holiday, vacation, then came back. Man, what happened? What happened was, as the size of the skull was increasing, at some point it has reached a limit where babies who are born with bigger skulls were getting stuck in the womb, right? And they're dying inside. While giving a delivery, right? The people with the bigger skull, the kids with the babies with the bigger skull, either are getting stuck or during giving delivery, right? The skulls are getting deformed. So all these kids with the bigger skulls are dying. So evolution has stopped from the skull from growing a certain size because that is become the limitation. Technically speaking, growing a bigger skull is better, but there is another limitation now which is killing this babies there. But then what changed in 1980s? Chalo fine, that is great, that is understood. But 1980 was suddenly kya ho gaya? Skull decided like, yaar, chalo, let's done, I'll get out somehow. Cesarean operations. People stopped giving birth naturally. Now we start cutting the tummy and take out the baby, right? Now we don't have a problem. Now the skulls can become bigger. Again, the skull growth started going up. Did you see? We did affect the evolution. So now if you compare a person ka skull 100 years back, before 20s and now, you will see we are slightly bigger. And it is still going on. The skulls keep getting bigger and bigger, right? So when I say this, people imagine like this, huh? The bio people think our heads are going to become like this. Something like an alien does. No, that's not how you're going to look after maybe, even after 1,000 years, it still look normal only. But yeah. So let's see this thing. What is this cube square law? It's pretty interesting that way, you can relate a lot of stuff to a lot of things. It makes sense. You can explain a lot of things. The small temperature difference. But this cube square law is quite important for architects, for especially designing stuff and all this. even for evolution. So when you say small temperature difference, delta T is temperature of the body minus temperature of the surrounding. If delta T is much, much less than temperature of the body and temperature surrounding, when I say much, much less than, let's say temperature of the body is 30 degrees, temperature of the surrounding is 27 degrees, delta D is 3 Kelvin, which is much, much less than 303 Kelvin. You're getting convert everything in Kelvin. So don't compare 3 with 30. You should convert into Kelvins. With respect to 300, 3 is small. It's 100th, 1%. It's very small. So what happens? Now, if you look at your Stefan's heat exchange thing, dq by dt is minus sigma A E TB power 4 minus TS power 4. Minus sigma A E TB will be TS plus delta T to the power of 4 minus TS power 4. Take out that TS common. Sigma A E TS power 4. You end up with 1 plus delta T by TS to the power of power 4 minus 1. Hope you remember binomial approximation 1 plus x whole power n can be approximately written as 1 plus nx if x is very, very small. Delta T is much, much smaller. This will be dq by dt is minus sigma A E Ts power 4. This is 1 plus 4 delta T by Ts minus 1. 1 cancels off, 1 Ts will go off. You end up with dq by dt is minus 4 sigma A E Ts cube delta T. There. So what you get is the amount of heat a body loses will depend on proportional to the temperature. More than that, it is proportional to the area A, which is proportional to 4 pi r square for a sphere. So how much heat a body loses will depend on the surface area. This is okay, but we have something more interesting. dq by dt can be written as ms dt by dt, which is minus 4 sigma A E Ts cube delta T. So we have dt by dt. One sec. Huh? If you have dt by dt, this is minus 4 sigma A E Ts cube pi ms delta T. This is proportional to area by mass. And for a sphere, area is 4 pi r square. And mass is rho 4 by 3 pi r cube. So this is proportional to r square by r cube. That's why this is called a cube square law, which is proportional to 1 by r. I'll show you a question on this, then we will discuss in detail, like how does this really affect stuff? So we humans, right, we are not actually interested in heat losing per second, we are interested in temperature. Quite a useful one. Cube square law. There's a cube and a square. I think you can copy it on this part at least. The one I circled, those are important. You can put it down. You should definitely remember them. Derivation is not important. Exam, you won't have time to derive all this stuff. But this much you should have an idea. You can remember valid only for small temperature changes. Clear? Let me show you a question and then we will talk about this. So we have a sphere, radius r, 2r. Everything is same temperature and everything. So two spheres of same material and temperature. But radius is different. So the first question, who loses more heat per second? Second one, who loses more temperature per second? Let's get this. Just give me a minute, give it a try. Let's see. Now, the general thing now, people think, sir, if you're losing more heat, shouldn't you lose more heat? There's a difference. It's like just because you lose more, let me give you an analogy. Think of like this. Let's say I have a big container and I have a thin container. In this big container and this thin container, let's say I have same water up to same height. Now from here, if I remove 10 liters, the water level will only change like pretty little. But from here, if I remove 2 liters, the water level will drop this much. If you see the first one, even though I lost more water, I lost more height here. You get the difference? Just because you lost more water doesn't mean you lose more height. So heat and temperature are like this. Heat is like volume, amount of water. Height is like the temperature. Are you getting the difference? So a body can lose more heat, but can lose less temperature. Now in this question, if you look at the thing, the first one, dq by dt, which is minus 4 sigma ae ts cube delta t proportional to area proportional to r square. So the bigger the body, more heat it will lose. So bigger sphere loses more heat. At least initially. If you look at the B one, this is dt by dt minus 4 sigma ae ts cube delta t by ms proportional to a by mass proportional to r square by r cube proportional to 1 by r. So smaller the body, the faster it will lose temperature. So the smaller sphere cools down faster or loses more temperature per second. So there is something important for us here. That means as the size of the animal becomes bigger and bigger, it will have a problem with temperature control. And we know for biological things, right, the temperature control is one of the very important things. Meaning in human body, if you see, the two things the body always fights to make a constant is one your pH scale of your acid and one is the temperature. if your temperature of the body tries to change, your body will literally fight back. And the same reason, if you get a fever of 104 degrees of Fahrenheit or whatever it is, and if you go to the doctor, you know what the first thing they'll do? They'll put you in an ice tub. They won't even care. Why are you getting such a high fever? We'll see. We'll think about that later. First, let's cool you down. Because if your body temperature exceeds 43 degrees, your brain cells start dying. We're just talking about 43. Yeah? Summer mein, Mumbai mein temperature does go to 45, 46. So if your body temperature exceeds 43, the body will do all kind of things like fainting, sweating. It will try to maintain. 43, you're in a death zone, you're gone. So normally your temperature is around 36.9, 38, right? Roughly, something around that range. That's like 5 to 6 degrees and we are gone. So now if you look at the animals, right? Like look at maybe a dog. If you look at a dog, did you ever see it puts the tongue out and it breathes in and out? I used to think the dog is smiling at me. When I was a kid, so that's what I used to think. The dog is happy and it is smiling at me. So that's not the reason. Dogs are generally happy. You should see the tail if they were happy. The tongue thing, right? When it gets really hot, what the dog does, it is breathing air in and out of the mouth. It is actually using convection to cool down its body temperature. Getting it? So next time you see a dog putting the tongue out and breathing, don't think it is smiling. It's actually breathing in and out to maintain temperature. Getting it? Now, if you go to little bigger animals like lions and tigers, if you see, they also have a problem. Animals become little bigger, they have a problem with temperature control. And if you see, that's why lions and tigers, they love water. They always try to stay near a lake or a pond. They keep rolling in the mud. If you ever gone to a zoo, if you see them, they always love to play in the water. Again, because the body becomes really uncomfortable. Now, when you come to little higher, if you look at, what stops a cheetah from running very fast? Body gets overheated. It can run very fast, but it can run only for a very small time interval. If it continues to run at a pretty high speed, the body gets overheated, it shuts down. So what stops cheetah for running faster for a long time is the body control. The temperature control goes exceeding. So if you look at humans, right, we are a little bigger, but then again, we are special little. We have sweat glands. When the body temperature rises beyond a certain levels, we start sweating and the system cools down. Now, if you go a little higher to elephants, look at the elephants. If you ever seen elephant skin, look at your skin. Look at elephant skin. Your skin is tight. Ever seen elephant skin? It has a lot of loose skin. Why it has a lot of loose skin? Again, the same problem. The elephant is trying to increase this area in the numerator. So as the size of the animal becomes bigger, it needs more surface area to cool down. So one way to do that, elephant has more folded skin. If you see an African elephant, they have big ears. Again, same reason. They're trying to increase the surface area, right? And when you have big ears, the blood flows through these blood vessels. It becomes more easy to cool down. So this is what actually stops from an animal becoming bigger. As the animal becomes bigger and bigger, it'll have a problem with the temperature control. If you have a problem with the temperature control, your enzymes won't work properly, your body functions will cease. So it becomes diseased, it will die early. So elephants don't grow beyond a certain size. But then, ever heard about this thing, mammoth? Saw Ice Age movie, the mammoth? These things are much bigger than a regular elephant. But when did they live? Ice Age. They didn't have a problem with temperature control. That means by global warming, you can clearly from this logic, as the global warming increases, the size of the animals actually will decrease. So during cold, the size of the animals becomes bigger. And again, this takes over a long span. Now then how does a blue whale grow to such a big size? Where does blue whale live? Water. Ever happened to you in winter? You took a bath, you came out, when the water is on your screen, it feels really cold. Water absorbs heat 25 times faster than air. So a blue whale doesn't again have a problem with the heat control. So water animals in the water, right? They can grow to much larger sizes than compared to the animals on the land. So what dictates the size is your cube square law. This is an evolution. Now, if you talk about a motorbike engine, right? In a motorbike engine, when you design, right, we have a triangle. You can have power, you can have cost, you can have size. You can choose to. You can't have all three. You want a powerful engine with a small size, cost will increase. Because if the engine is powerful, it generates a lot of heat. And if the size is small, it can't radiate heat, so it will melt. So you need to use better alloys and better conduction materials, which will increase the cost. If you say, no, cost is a problem, but you want more power, less cost, then size will increase. Ever seen Enfield engine? Enfield bike, they are damn heavy it is. right? But if you hit it, you can hit 200 kilometers per hour. Senior scooty, you try to put almost like full throttle, you won't even reach 70. It'll struggle at 70. It is like it's making all kind of weird sounds. Right? If you say no, I can't fit too much cost and I want small size, then compromise on power. Getting it? So when you're designing a motorbike or electric motor, any engine, this is one of the things which stops you. You don't want a big bulky engine on the bike, right? It doesn't look good. You need to put more space. Bike becomes bigger, heavier. But then again, you don't want the bike to be more costly also. So that is a difference between an F1 race car and a normal regular car. In F1 race car, cost is not a problem. F1 race car, cost is not a problem. So they'll do every damn thing that is possible. I mean, just to give you an idea, in F1 race car, they freeze the fuel to minus 40 degrees and then they inject it. You know that? You know why? In F1 race car, right, they have a regulation. The size of the tank can be only 230 liters. It has to be 230 liters, not more, not less. You're getting it? So, or else what will happen? Everyone will make different cars. So F1 has pretty strict regulations. The size of the car, the width of the car, everything has to be up to a certain limit. So what these people do smartly, the volume of the capacity is 230 liters. So they will freeze the fuel to minus 40 degrees. What will happen? It will compress. Then they inject the fuel. So as the race is going on, fuel gets over, right? And the fuel starts warming up. This is equivalent to 270 liters at normal temperature. So the car needs to come to the pit stop much less. So in the pit stop, you save time. That's almost 10-15 seconds. That will give you more advantage in the race. Now in F1 race cars, people don't use normal fuel. They take the fuel, they freeze it to minus 40, then they inject into the oil tank. See how crazy they are. They don't have a problem with the cost. So if you're running an F1 race car team, you will go bankrupt. The car itself costs you around 10 crores. If you can make it vertical and put some wings, it'll fly like a rocket. It has so much power. Same thing happens when you're designing buildings also. If you make a building big, right? Solid building bana diya. You put a lot of rooms inside. The people in the middle, right? They will die with heat. There's no ventilation. So when they design buildings like this, what is the general idea? No one designs building like that. They'll put a building here, building here, building here. They'll put buildings like this. No one designs one big cylinder. So there, all the stuff goes there. This is the cube square law. It tells you why animals don't grow in size. It tells you why you can't design efficient engines or cost will increase. It tells you why buildings can't become more and more cramped. It explains a lot of stuff. It tells you why Godzillas can't exist. If really a Godzilla exists, the size is so big, the Godzilla will get fried inside. You'll get a tandoori Godzilla. I mean, it will get cooked by its own heat inside. It'll get so high temperature. Ant-Man cannot exist. When the size increases, the stress increases. The moment Ant-Man becomes 100 times bigger, his legs will have 100 times stress. He will get a fracture and die. So their Ant-Man movie is bullshit. But then again, fine. He's a fun person, so let it be. So there are a lot of inconsistencies if you see, even in Avengers. Hulk is a big inconsistency. So when the Hulk becomes big, if this mass guy is let's say 60 kg, Hulk is suddenly 500 kg, where did you get the extra mass from? Hulk disobeys law of conservation of energy. And whenever Hulk becomes normal, what happened to all that energy or mass gained? From E is equal to mc square. Every time Hulk becomes bigger and smaller, it is like a nuclear bomb exploding, isn't it? So every time Hulk expands, all the energy in the surrounding will get absorbed and Hulk becomes big. Everything will freeze. When he becomes normal, he will explode and the entire area gets blasted. So Hulk is not really, technically it doesn't work. So if you look at all the heroes, right, I think in Avengers also the only sensible hero set is that Hawkeye. Right, remaining all our Captain America is still fine. You could have same mass, but if you have same mass, that means his density has decreased. That means Hulk will float like a balloon. Meaning, this is a concern even I had, if when you look at an Ant-Man, where Ant-Man has become 100 times bigger. So my question is the mass constant or density constant? If you say mass is constant, fair enough, mass is conserved. That means its density has become rho by 100. Now the ant-man will float like a balloon. If you say no, density is constant, then the mass has become 100 times. Where do you get the extra mass from? So either way, Ant-Man, I couldn't fit him anywhere. So yeah, he doesn't work. But interestingly, he's the main link between the Avengers movie. He's the one who saves everyone. So, anyways, getting back to it. So we used to have all these kind of pointless fights when we were in college. I used to support Batman. I used to say like, Batman is a proper superhero, and his power is what? Being rich. Batman ko superpower is being rich. So that's how it works. That is a bit of a radiation there. Cube square law, quite an important one. Do check it out. Next thing, Wien's displacement law. So normally we used to thrash the people, who say Superman is a good hero. For some reason, we used to hate him. We all are fans of Batman, though. I even proved that Batman kills people. And we proved when it is pretty simple. Like, think about it. Someone is falling from a height, the Superman comes and just catches him and goes. So when you actually calculate the change in momentum, the person who got caught, he will feel as if truck has hit him at a speed of 200 kilometers per hour. No one is going to survive. When Superman catches you, you're not going to survive. It's as good as hitting a concrete floor. So there. So what is this Wien's displacement law? This is a good one. So when a body emits radiation, it's emit photons in all wavelengths. Getting it? It doesn't just give one single wavelength. It just gives you wavelengths of different things. Now in this, a certain wavelength. So let's say when you switch on the bulb, it is giving photons of 4,000, 3,000, 5,000, 8,000, different photons there. So what this thing says is a particular wavelength lambda m contributes maximum energy. I'll give an example also. So this lambda m, this wavelength where you get maximum energy into temperature is constant, experimentally derived. So this lambda m, which contributes maximum E lambda. What is E lambda? Spectral energy density. The energy, given at a given wavelength, energy emitted at a given wavelength. T is the temperature. Again, T is always in Kelvin. So for black bodies, this constant becomes 2.88 into 10 power 3 meter Kelvin. But let's see a little more detail exactly what this means. You can put on this formula, like I'll show you again and then I'll write that on again. So when you actually plotted the graph, so you're plotting the energy given by every wavelength versus wavelength lambda. The graph kind of looks like this. Can you see this? This looks like Maxwell distribution of velocities. The Gaussian, the normal distribution. I keep saying this thing just pops up everywhere, wherever there's a huge sample. So what this Wien's displacement law says is there is a particular temperature, wavelength lambda m, which gives you this maximum spectral energy density. Let me give an analogy. Think of like this. Let's say you have some money with you, but all the money is not in one single currency. You have denomination 1 rupee coins, you have 2 rupee coins, you have 5 rupee coins, you have 10 rupee coins, and let's say you have 20 rupee notes. This is the number of coins. This is the money that you have. So let's say you have 1,000 coins, you have 2,000 coins, you have 5,000 5 rupee coins, you have again 1,000 10 rupee coins, and let's say you have maybe 400 20 rupee coins. Now you tell me, how much is 1 rupee contributing? 1,000 rupees. 2 rupee contributes 4,000. 5 rupee contributes 25,000. 10 rupees contributes 10,000. This contributes 8,000. So my question is this: the total money that you have, which denomination is contributing maximum amount? 5 rupee coins, right? You're getting this? So here the denomination is similar to wavelength. So whenever a light is emitted, it is emitting wavelength in different wavelengths: 4,000, 3,000, 5,000, 7,000, 8,000. In that, a particular wavelength is contributing more. Similarly, look at this. You have money with you. The money that you have 1 rupee coin, 2 rupee coin, 5 rupee, 10 rupee, and 20 rupee coins. The 5 rupee coins contribute maximum amount of money. So this guy is similar to lambda m, and this guy is similar to E peak. Doesn't making sense? So this is just an analogy. So here the 5 rupee coin contribute maximum energy. This is similar to lambda m gives maximum E peak. And the number of coins is like number of photons, and this money is nothing but E lambda. This is the money in a particular denomination. Now tell me one thing, if I add all these E lambdas, what will I get? This will give you the total money, isn't it? This is similar to total energy. This is similar to total energy dq by dt, which is sigma a e t power 4. So that means if you add all the energy given by each and every wavelength, shouldn't you get the total energy emitted, which was the Stephen's law sigma a t power 4? Is that making sense, everyone? Is this diagram making sense now? So what this graph tells you is the photons with high wavelength give less energy, photons with low wavelength give less energy. Most of the energy is contributed one in the middle, the average. And in that also, there is one particular wavelength lambda which will contribute the maximum amount. Any doubts on this page? Anyone confused with the analogy, please ask. So this is one thing. Whenever you talk about energies and stuff, money, right, it has a lot of resemblance to energy. So here now, if I take the E lambda is again the spectral energy density. Energy per second at a given wavelength. So if I say integral E lambda d lambda lambda 1 to lambda 2, so if you integrate this area will give you energy per second emitted by photons from wavelength lambda 1 to lambda 2. Suppose if you take E lambda d lambda and put 0 to infinity, this will be the total energy. Means you're adding each and every energy, total energy per second. This is nothing but sigma a e t power 4. This is nothing but area under the curve. So if you calculate all the area under the curve, that will be sigma a t power 4. There, have a look at this page. Everyone can see my slide, right? Any doubts on this? Janil, can you see now? All got the analogy? No. Could you go to page 74 here? Clear enough, Pratik? No. Let's talk about that lambda mt again. So this thing says lambda m. So there is a particular wavelength at a particular temperature which contributes maximum amount. Now look at here. So if temperature increases, the maximum contribution lambda m decreases. It kind of makes sense also. As the temperature increases, the molecules move faster and faster. So when they collide, they release more energy. If you release more energy, then the photons will have less wavelength. Does that make sense? What is energy for photon? Hc by lambda, no? Less wavelength means more energy. So a blue photon has more energy than a red photon. Did you get the story again? Higher the temperature, the molecules move more faster. So when they collide, they lose more energy. When they lose more energy, right, in the form of photon, the photons will have less wavelength. Is that making sense? That means now you tell me, when you switch on the flame, what is fire exactly? Ever thought about it? What is fire? Fire. What is fire? We see that every day. So fire is nothing but what? Hot gas. Right, Vihan? Fire is nothing but a hot gas or a heated gas. Simple as that. So what happens when the temperature of the gas exceeds a certain level, right? First thing, they start emitting different kind of photons. So initially photons will be in infrared, you can't see. But if you increase the temperature more, they start emitting red photons, so you'll think the flame is red. If you still keep increasing the temperature, then the flame becomes orange. If you keep increasing more, then it becomes more. So next time you can observe this, after the class, you can just go and switch on the gas stove and observe it. You will observe when the flame comes out, initially the flame is blue. As the flame goes away from this thing, the flame becomes more yellowish and reddish. Observed? The reason is simple. The flame here is pretty hot. Since it is hotter, wavelength is less, you're more towards blue. But as the gas rises up, it cools down a bit, temperature decreases, it becomes more yellowish. Is this making sense? So this would kind of look like this. There. Can you look at this? This is a heated metal. This is 1400 degrees Fahrenheit, almost reddish. 1800 yellow, 2100, this thing, 2400 becomes white. That's the order there. 1400 degrees Fahrenheit. So I think that must be around, I don't know. How much is that? Around 600, 700 Celsius, I guess. Blue, you need more than 4000 degrees to see. Blue is damn hot. So that is one more question that we have. Now, this was a question in one of the exam. If temperature of the body continuously increases, can you tell me which colors you see? If temperature of the body continuously increases, the first color you will see is red. Then you will see yellow, orange. Then you will see white. Then you will see blue. What is happening? People get confused actually. They think like first you will see blue and then you will see white. No, we are saying 6000 is 4000 is for metals, right? Sun is a different story though. Sun you're not emitting because of, it's not conduction, right? It's not molecules colliding with each other. It's a gas. So what is happening here? Look at this. When you're heating it at low temperature, here you are getting red plus infrared. But infrared we can't see. So you think it is red. Then if you keep heating, then this will be a red and yellow. So you will think, okay, it is reddish, yellowish. Now, what is white exactly? White is not a color, you know that? White is not a color. When you say white, it is simply all wavelengths. That means when the body emits VIBGYOR, you get white. This is all wavelengths in visible region. So white is nothing but, so if you get all these colors, we call it white. If you keep still increasing more, what will happen? Now you'll start getting blue plus ultraviolet. Red will vanish. You'll get blue plus ultraviolet. Can you see blue? Can you see ultraviolet? You can't see. So you'll see blue. You getting the catch? From that entire spectrum, if you remove red and yellow, right, and then you get blue and violet, the color will start looking more bluish, isn't it? This is the reason why you'll see first white and then you'll see blue in the last. So if you still keep heating, then what will happen? Even blue will vanish. Everything will be ultraviolet. You can't see anything. It looks dark. But technically, the room is actually very bright. It's emitting a really high energy. You can't see. Is that color scheme making sense, everyone? Quite an important question. Easy question. People goof up. Most people write red, yellow, blue, and then white. But this is the order. You'll see red, yellow, white, and then blue comes last. Okay. Let me show you something. The temperature is not the only thing. You also need to see what kind of material. Is it a gas giving or solid is giving? Metals at a lower temperature also, right? They can give you this. For example, if you look at your bulb now, the bulb's ka tungsten filament goes to almost 4,000 degrees. Pretty inefficient. They give us so much heat, right? Only like around 5 to 10% gives you light. That's the reason now it is almost like you can say literally unofficially it is banned. No one uses bulbs now.
Two things happen. As objects become hotter, two things happen to the light that they emit. The first is that they start emitting more light at every wavelength, at all the different colors at which that object emits. It gets brighter. The second thing that happens is that the peak of the emission shifts from the red all the way up through the blue. It goes on even further than that if they get hot enough. So in other words, the object changes color. You're a little bit familiar with this if you've ever used a Bunsen burner, because the flame on your Bunsen burner was blue in the middle and it was red on the outside. And if you wanted your chemistry reaction to go fast, you stuck the bottom of the test tube down in the blue part of the flame, because that's where the flame was hotter. And if you wanted the reaction to go slow, you stuck the bottom of the test tube in the red part of the flame, because that's where the flame was cooler. I have here an incandescent bulb that I can use to demonstrate this same effect. Now I'm going to point out that we have two cameras. One of those cameras is fitted with a filter that just filters out some of the light. So when you see the light bulb through that camera, it's going to look fainter so that you can actually see the color better. But the other camera is early.
So what she's doing, right? So that is a current passing through the bulb. Studied in school, right? I square R, remember? Power. So more current you send, more heated up it gets, more temperature. It becomes
I'm going to start
light.
by turning this giant dimmer switch just a little bit so that there's a little bit of current running through the light bulb, and we'll see that it lights up, and we'll take a look at the color. So here the light bulb is barely lit, and you can see that it's red-orange. It's a very reddish color. This is almost exactly the color of Betelgeuse, one of the stars in the night sky. If I add more current so that the filament gets hotter and hotter and hotter, you can see that the red goes away and the color becomes dominated by yellow. If I continue on and I go past that point and I keep heating up the filament hotter and hotter and hotter, you can see it gets much, much brighter as it gets hotter, but then it also turns bluer as it gets hotter. Until here, this is as high as I can go with this particular.
So this equipment can't go higher than this, so we can see white. But if you can send more current, it becomes blue.
Particular light bulb, and you can
This
see
is how
that
it
the
looks.
color.
If you can actually go higher, this is how the filament looks. Can you see the room is so dark? That's because it is only giving blue and maybe ultraviolet. This is the order I was saying. So first you'll be red, yellow, white, and then you get blue. The filament becomes like this. Clear? I'll post this video in the group. You can check it out more detailed. Clear with this? Now, this is like a concept and a theory also. So let's say if I'm drawing a graph for E lambda versus lambda, let's say this is a graph for temperature T. Can you draw the graph for 2T? If the green one is the graph when the body का temperature is T, same body when the temperature is 2T, उसका graph कैसे दिखेगा? Try, I'll give you a minute. Pretty standard question in mains. They give you the graphs and ask which is the graph for T and 2T. So if T looks like this, 2T will be what? Now, I'll write down all the main formulas that you need. First thing, what happens to lambda m? So this was the first thing. So lambda m into T is constant. So if the temperature becomes double, your lambda m becomes half. The second thing, the area under the curve, the area is root over 0 to infinity E lambda d lambda, which is sigma A E T power 4. So the area is proportional to temperature to the power of 4. That means this area here will be like this 16 times bigger. Third, the E peak, now this is experimentally derived. So E peak is proportional to T power 5. This is again pretty rare formula where in physics you have a power 5. That means if this is E peak, when you double the temperature, this guy gives you 32 times E peak. There, these are the three main things I can ask you: lambda m, area, and the peak value. So the graph will shift to the left, so you'll get much higher energy at lambda m by 2. So area at T by area of 2T will be 1 by 16. E peak at T by E peak at 2T will be 1 by 32. Important graph. You should definitely know this. You can expect this in mains or bits or some exam. Is this making sense? Clear, everyone? That is there. Let's see a few problems on this also. Take a break. Come back to 7 o'clock. We'll continue from here. Any doubt so far? Chalo, come back in 10 minutes. Yeah. Let's see a question on this. So we have a E lambda versus lambda graph, and there are three equal areas, A1, A2, A3 are given. So the question is, N1, N2, N3 are the number of photons emitted per unit time corresponding to each area. So arrange N1, N2, N3 in ascending or in descending order. Be careful here. First thing, what did he say? The area is same. What is area? Area, which is E lambda, D lambda. Don't get confused between this. Need to notice one thing. He didn't say same width. If you take same width, the center area would have been the biggest. Did you see the center area is very thin? So they have same area. So E lambda, D lambda, that will give you the energy per second. This is same for all because area is same. So we get confused thinking, oh, center one will have more energy emitted. True, if you are taken same width. So what is energy per second? Energy per second is nothing but number of photons per second into energy of each photon. So this is nothing but number of photons per second into energy is hc by lambda. This is some constant. Oh, this is area. So from here we can clearly see n by lambda is constant. So n is proportional to lambda. So higher the wavelength, more the number of photons, n3 greater than n2 greater than n1. Meaning, think about it logically, it makes sense. Simple thing. See, imagine you have 100 rupees, I also have 100 rupees. We have same amount of money. I have everything in 1 rupee coins, you have everything in 2 rupee coins. Who has more coins? The least denomination, isn't it? If the wavelength is more, A3 ka wavelength is more, means energy is less. So to compensate, you need to have more photons. Does that make sense? If you and I have same money, but I have 1 rupee coins, and if you have 2 rupee coins, I will have more coins, even though our money is same. Is this making sense, everyone? So higher the wavelength, lesser the energy. Lesser the energy, you need more photons to compensate. Clear with this? Any doubts on this? And be careful, he didn't say same width. Suppose the same question, if the question was like this, if the width is same, then what would have been the answer? Tell me, I'll give you 30 seconds. The question was, there's not equal area. If they have equal width, now can you say anything about N1, N2, N3? Think for a minute. Now we have issues actually. If you take same width, Who has the maximum area? A2 is the greatest. Then comes A1. Then comes A3. Agreed? Makes sense? And what is area proportional to? Area is N2 lambda 2 greater than N1 lambda 1 greater than N3 lambda 3. So if you want to compare between 1 and 2, who has more wavelength? Lambda 2 is bigger. And this is greater sign. You can't really compare N2 and N1 actually. You can't compare N2 and N1. Between lambda 1, lambda 3 is bigger. That means lambda 1 is smaller. So, but you're saying N1 lambda is greater than N3 lambda. So therefore, definitely N1 is greater than N3. This much we can say. We can't tell anything about N2, I guess. Is that making sense? So you have two inequalities, right? You have one this, and another inequality is this. Lambda 3 greater than lambda 2 greater than lambda 1. So using these two inequalities, you have to figure it out. I don't think you get any relation between N1 and N2. N1, N3 you can figure out, not N1, N2. Clear with this? So the problem here is now we don't know like how much the energy of the photon. Lambdas are not exactly given. Clear with this question? Let's see one more. Let's get this. Two bodies A and B have thermal emissivity 0.01 E. Thermal emissivity is that E ka value. Read this. I'll give 2-3 minutes. Let's read the question. First thing, there are a few words here. The outer surfaces of the bodies are same, meaning they have same material. The radiant power is at the same rate. So he's saying dq by dt sigma a e a t a power 4 is equal to sigma a e b t b power 4. So this is 0.01 Ta power 4 is 0.81 Tb power 4. So from here we get Ta is equal to 3 Tb. So Tb is Ta by 3, 1934 Kelvin. That is the first part. Then he's saying the wavelength lambda b corresponding to maximum spectral radiation blah 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 b is shifted from the wavelength of A by 1 micrometer. So he's saying the difference between them, lambda, whoever is bigger, who is bigger? A is bigger. So lambda b minus lambda A, the difference is 1 micrometer. Micrometer is 10 power minus 6. And we also know lambda A Ta is equal to lambda B Tb is equal to constant because it's the same material. And lambda A and lambda B is given. So Ta will be 3 lambda A is equal to lambda B. Take this guy and substitute in this. So you end up with lambda B minus lambda B by 3 is equal to 1 micrometer. Therefore, lambda B will be 3 by 2 micrometer. Check. There, that's how they combined the Stephen's law with the Wien's displacement law. This was an old PYQ. Check this out. Clear? Any doubts on this? Next thing. So that is about radiation. So if you see in radiation, we had Stephen's law, and then we have Wien's displacement law. These are the two primary things. The third one is convection. But like I said, it is removed from the mains portion. At least that's what they said. But they gave it in the exam, like on 29th, it came in the exam. So now we have to see what they're going to do. Are they going to give it bonus or what nonsense they will do? But let's see. But in advanced ka portion, they clearly wrote it is there. So we will do it anyways. Because bits may be here. It is there in your boards also. So better we do it. We can't trust this JEE mains people. So convection. So convection is actually one difficult thing to study. You can't actually define a particular formula or anything. Depending on the shape, the size, and the surrounding nature, the material, and all, things change very badly. So whenever we have to study convection, people literally make a model out of it. They put it in a lab, they test it and do it. So you can't study it theoretically. We do have one case where it is little, you can study a bit. So in convection, the heat transfer is due to transfer of material. Like I said last time, if I have to give you pen and if I'm standing here, I can pass on the pen, conduction, I can throw the pen, radiation, I can walk and give you the pen, convection. That's a simple analogy there, right? So what happens in this, one of the most common example that people give is this boiling water. So let's say you put a flame here and you're boiling this. So heat transfers from bottom part to the upper part. This is conduction. And then what happens? The water gets boiled up. So the hot water rises. Because as the water gets heated up, density decreases, it rises. As it comes to the surface, it starts cooling down. As it cools down again, density would decrease. The water will start sinking. And the cycle will just keep on happening. So heat is literally transferred up and down due to the material transfer. this cycle will continue. So convection is very difficult to study, but we study a special case. Called forced convection. Forced convection, meaning the system is naturally not cooling on its own. Best example is this: when you're drinking tea or coffee, hot tea or coffee, how do you drink? You blow air, right? You blow karke and then you drink. So what you're doing, you're forcing the system to cool down. It's not cooling naturally. So this is called forced convection. So if you have, let's say, a bowl of hot soup, let's say you put it under a table fan or something. So now you're forcing the system to cool down. This is forced convection. There's only one formula we have, and the remaining thing kind of looks more like a maths than physics. But let's see what is it. So convection we study. So in this, the law is called Newton's law of cooling. So Newton's law of cooling is valid for forced convection. General in the question, they'll mention Newton's law of cooling. So what this thing simply says is the rate of change of temperature of the body is proportional to temperature difference between body and surrounding. So dTB by dt, small t is time, capital T is temperature, is proportional to TB minus TS. This is the temperature of the body, and this is temperature of the surrounding. So dTB by dt is minus B into T body minus TS. There. This is the formula you should know. B is some constant which we will not able to find. They have to give you. But most of the problems you won't need it. It gets cancelled out. So B is a constant. It depends on multiple things. It depends on nature of the material, the size, shape, humidity, temperature fluctuation, wind speed ka variation, a lot of things. So that's what I'm saying. It's very difficult to put everything in a theoretical way. Meaning, think about it. Let's say you are very hungry, right? And you go to the kitchen and the rice has just come out of the cooker. And when you take that rice and put it in the dump in the middle, do you put it like this, or what do you do to cool it down? You spread out the rice, isn't it? So when you spread out the rice, unit cools down faster. So it also depends on the surface area. Shape, size, etc. There, that is the only formula we have. You can put it down. So we'll just play around with that. So I'll show you a question. So that same question in advanced you do it in one way, in boards you do it in another way. So advanced one is more accurate, but boards where they use something like an approximation average method, you have to stick to that. It is there in HSC boards. Let's see the question. A body, temperature of the body is 2T naught. Temperature of the surrounding is T naught. Assume Newton's law of cooling. So exactly what is the scenario, we don't know, but Newton's law of cooling is given. So that means dt by dt. So if you see here, the lower the temperature of the body, the lesser the temperature will fall. So TB is not constant here, it is continuously changing. Find the temperature of the body at time t. Let's get this. Just one integration. Get it? Initially your temperature is 2 T naught and outside is T naught. So eventually you will reach T naught there. You'll get answer in terms of law, na? Exponential में आ जाएगा. Can't get an increasing function. Did you take the minus sign into consideration? Then I can, yeah. Let's see. So dTB by TB minus TS is equal to minus dt integrated on both sides. Time is 0, temperature is 2 T naught. When the time is T, temperature is some T B. So this will be ln TB minus TS. Limits will go from 2T naught to TB. This will be minus BT. So this will be ln, substitute the values, TB minus T naught minus ln. Remember surrounding a temperature is T naught. So 2T naught minus T naught is minus B. So this is ln TB minus T naught by T naught minus BT. So this will be TB minus T naught is e power minus BT. There, so temperature of the body will be T naught into 1 plus e power minus BT. That's the temperature of the body, everyone. Now, sometimes they'll ask you to plot a graph. If you have to plot a graph between TB and time, then you're starting at 2T naught. You will never reach T naught. It will take infinite time. The graph is an exponential decay, getting closer and closer to T naught. That's how the graph looks. But if they ask you to draw the graph of a ln graph, ln TB minus T naught versus time, you will actually see a straight line. That's because ln TB minus T naught is minus D plus ln T naught. This looks like y is equal to minus mx plus c. It's a straight line. So you have to be careful which graph is being asked. Well, if I ask you t versus time, then it is an exponential decay. If it is a ln versus t graph, it's a straight line. Graphs are actually pretty good questions. They used to ask such things. Clear with this? Let's see the same question, but this time let me give you some numbers. Any doubts on what I did? Nothing, I just did maths, right? This is pure maths, there's no physics there. Once I wrote this formula, physics got over. You have to get used to that Lonka integration. Pretty standard one keeps coming. I'm pretty sure till now you must have seen at least this thing at least 8 to 10 times. Let's see one more. Now this question, let's do both the ways. So a body cools down from 80 degrees to 70 degrees in 10 minutes. How much time does it take to cool from 70 degrees to 60 degrees Celsius? Temperature of the surrounding is 30 degrees. Assume Newton's law of cooling. This is how they'll frame questions. Question is clear? 80 to 70 took 10 minutes. Surrounding is 30 degrees. 70 to 60 will take how much time? Do you think it will take less than 10, more than 10, or equal to 10? Should take more, right? As the body temperature becomes lesser, it loses heat at a slower rate. So it should take more time. That much we know. Solve. Let's see. 12.5. How did you get such a good number? Eh? 750 seconds. Okay, let's see. Let's see. I'm not sure how you got such a good answer. So dt by tb is minus b, tb minus ts. Integrate this. So this will be initial temperature. This is final temperature. This is 0 to t. So this will be ln T final minus Ts by T initial minus Ts is equal to minus Bt. So for the first part, when you go from 80 to 70, the formula is ln T final is 70, surrounding is 30, by initial is 80, surrounding is 30. This is minus B and time is 10 minutes. When you go from 70 to 60, ln T final is 60 minus 30 by 70 minus 30. Time we don't know. Divide them. This is 1 and this is 2. If you divide, you can just shift the minus sign or divide 1 by 2. This would be ln, that would be 4 by 5 by ln 3 by 4 is equal to 10 by t. So we get time is equal to 10. This is ln 4 by 3, multiply numerator denominator with minus sign. This is ln 5 by 4. Ln a by ln b is nothing. We can't solve this. Not sure how you guys simplified this. Is there any way to simplify this? I don't know. There's no formula for ln a by ln b, na? Is there? So that's it. You're stuck here. So this comes in the exam advancement. They have to give you the ln ka thing, or they have to give you options in terms of ln. How did you get good numbers? Someone got 56 minutes. You are living in some other planet. But I think if you solve this, you will still end up around 12.8 something you will get. If you have a log table. So, okay. Clear with this? This is how you actually solve. You'll get everything in lns. But there is another method that you can use. It's an approximation, which we actually, boards where they do that only. You can't solve like this in boards. Going ahead. Again, if you see there's nothing there other than max. The alternate method. So the idea is this. The temperature of the body with respect to the time, we know it is just decreasing exponentially. So if you take a small slice of it, small temperature change, we can assume the temperature to be a linear function here, which is actually it is not. Function is linear for small temperature change. It does give you a decent answer with a very small error, but the temperature should be small. So we can use average method. So this is alternative. So we use average temperature for a body. Meaning, see, when you go from 80 to 70, it took you 10 minutes. You want to go to 70 to 60, you want the time. Temperature the surrounding was 30 degrees. So what this method says, right? Now the problem here that is happening is since body ka temperature is changing, it has become a variable. So here you take T body ka average 80 plus 70, 75. You take the average temperature 65. So you assume the body is losing heat at a constant rate. Assumption. So this is how the formula goes. So dTB by dt is minus B. Now this will become TB average minus T surrounding. So for the first one, 80 minus 70, time taken is 10 minutes, minus B, average is 75 minus 30. For the next one, 70 minus 60, time I don't know, minus B, average is 65 minus 30, divide them. This will be 10, 10 will cancel. 10 by t. T by 10, I guess. How much is this? I can actually substitute. And let me divide them. So b will be minus 1 by, that is 1 by 45. Take it and bring it here. So this is 10 by t, 1 by 45 into 55. No, not 55, 35. So we get t is equal to 10 into 5 nines are 7s are 90 by 7. This comes to around 12.8 minutes. If you actually solve that ln thing, that I think will come 12.83 or something. I'm not sure, but you'll get an error in second decimal. So using the average method, right, we get an error in the second decimal. But if you see, this is more convenient. You need not use any lawns and anything to figure out the value. But boards may, this is what they expect. But logically speaking, this works. It works. But this problem also has some limitations when you're using approximations. First thing, this does not work if the temperature difference is large. The lawn method still works. This method fails if temperature difference is large. Second thing, it fails if the temperature of the body is close to surrounding. Because think about it, as the body temperature goes closer and closer to the surrounding, it takes infinite time, isn't it? If temperature of the body is close to surrounding, meaning if the body temperature gets close to 30 degrees, this will fail horribly wrong. There, have a look at this method. So it is easy to figure out. Exam may look at the options. If all the options are in terms of ln, they're asking you to integrate. If you have proper numbers and they didn't give you ln ka values, he's asking you to do the average method because they won't give you a log table in the exam. Boards may, they'll expect you to do this method only, average method. They won't expect you the integration. Clear? Clear with the average method? Any doubts on this? Let's see a question. Let's see a question. A body cools down from 100 to 90 degrees Celsius in 10 minutes. Temperature of the surrounding is 20 degrees. First question. How long does it take to go from 90 degrees Celsius to 80 degrees Celsius? This is the standard one. So I want the time here. Second question, find the temperature if the body is cooled for another 10 minutes. So if I give same time, then what will be the temperature? Meaning you're going from 100 to 90, took you 10 minutes. From 90, if I give you another 10 minutes, then what will be the temperature? You're getting how can I frame the question? I can play both the ways. I'll give you the temperature and ask you time, or else I'll give you the time and ask you the temperature. Get them both. These are the two models you have. Using average method. Okay, then I'll give 2-3 minutes. Using average method, you can figure out the values. 11.2 nahi hai, solve properly. Integer mein you have to put an answer up to 2 decimals. Let's see, 11.53, right, Ishana? Get this, everyone should try. I'll give another minute. First, you should have got it by now. Let's see. 11.53 is the answer, right? First one. You're going from 100 to 90, 90 to 80. This took 10 minutes. This time we don't know. So here the TB average was 95. Here TB average was 785. So the temperature difference, 100 minus 90 by time is 10 minutes, is minus B into TB average is 95 and surrounding was 20. For the second one, 90 minus 80, time I don't know, minus B, 85 minus 20, divide them. That would be 10 by 10, 1, and this is 10 by, again, which formula are we using? Just in case you forgot, we are using this guy, dt by dt is minus B, TB average minus TS. This is the one we are using. So if you divide them, you will end up with 1 by 1 t by 10, 75 by 65. That's 150 by 13. This is approximately 13 ones are 13, then 11, so that is 7. 1 and then 20, so that is again 13 ones. Then we have 70, 13, 5, 65. And then we have 50. That's approximately 4K aspas, so 13.53 minutes. Okay, 72.5. Array God, it took 11 minutes to reach 80. 10 minutes, shouldn't it be more than 80? What about the second part? You're going from 100 to 90. 10 minutes. 90 to some temperature, 10 minutes. T surrounding is 20. So T body average was 95. Here T body average is 90 plus T by 2. So here the temperature difference was 100 minus 90 by 10 minus B, 95 minus 20. Here it is 90 minus T by 10 minus B, 90 plus T by 2 minus 20. Divide them. You will get 10 by 90 minus T is equal to 75 by 45 minus 20, 25 plus T by 2. 5 2s are 5 15s are cross multiply. 50 plus T is equal to 15 nines, 1350 minus 15T. 16T is 1400, no, 1300. This guy is 81.25 degrees Celsius. Clear? This is how you do these two models. Either I can give you the time or I can give you the temperature and ask you time. So either way around. Clear with this? If they ask you in boards, CET, mains, bits, this is the model. Advanced may look at the options. If it is given in lawns, use the integration. Clear with this? More of a max. There's nothing there. You're just putting there in the formula and solving. Let's see one more. Any doubts on this? This is another way to ask. Read a question. Try to understand for a minute, then I'll explain you the question. The thing is, question understanding is the thing. The language will be a little weird, but let's try to understand, explain, you see. So what this thing is saying is we have a room here. So radiator meaning we have a heater inside the room. So the radiator will have its own temperature. Let's call it T rad. So generally when you switch on a heater, right, heater ka temperature remains constant. You normally maintain a thermostat like that. So in this process, what it does, it gives you some heat to the room. Then we have temperature of the room. And then we have temperature of the surrounding. Now outside, if it becomes very cold, what will happen? Some heat will escape. So the power given by the radiator or the power emitted is always proportional to the temperature difference. The more temperature difference you have, the more the temperature change will, the more the heat will flow. Clear? Now look at the question, what he's saying. He's saying when the outside temperature is -20, room ka temperature is 20. ठीक है. When outside became -40, your room temperature dropped. Kind of makes sense. Because if the outside temperature drops, more heat will escape outside. To compensate for that, the inside room temperature will drop. So how do we solve this? Look at this. Case 1. So there are two things happening here. We are getting heat from the radiator. So the radiator, so power we are getting radiator to room must be equal to power from the room to atmosphere or surrounding. So basically steady state, whatever you're getting from the radiator, everything is escaping out. And we know the power is proportional to the temperature difference. So let's take some constant K1. This is temperature of the radiator minus temperature of the room. So from room to surrounding, another constant K2. So K1, K2 is I don't know. This is temperature of the room minus temperature of the surrounding. So for the first case, K1, temperature of the radiator we don't know. Room ka temperature is 20. K2, room ka temperature is 20 and surrounding is 20. So this is 40 degrees. Same thing when you apply in the second case, we have K1, temperature of the radiator minus room ka temperature is 10. K2, now the temperature difference is 50 degrees. Divide them, K1, K2 will cancel. So T radiator minus 20 by T radiator minus 10, 4 by 5. Cross multiply, we will get T radiator is equal to 60 degrees. Yeah, that is the answer. This is another kind of problems they'll give you. So the radiator is emitting heat. See, how much heat comes out will depend on what is the temperature difference. If the room ka temperature and the surrounding temperature is same, then there will be no heat escaping. Making sense? This is another model of questions on Newton's law of cooling. Check it out. It's a good one. Clear? There, that is the last one on convection. So with that, we're done with the heat transfer, and with that, we also completed the entire heat and thermodynamics ka chunk. Chapter is quite a big one. If you see, we did thermal expansion, calorimetry, KTG, thermodynamics, and heat transfer. So you should start solving. In case you have not started, do start solving. Quite a big one. We did this for more than a month. You should have finished at least half of it by now. Don't delay it. Decent chapter, has a decent weightage. So with that, we'll wrap up for the day. So next class, when we catch up on Tuesday, we'll catch up at 5:40. We'll start off with fluid mechanics. I know there's a fluid and SHM. There are two things, but SHM is more difficult. Fluid is actually looks mostly like NLM. So I would feel that would be much better to do. I'm sure even in your classes they will catch up soon. So we will see. It should work out. So do start solving, right? Work on this, and remember there's a deadline.